Hi, my name is Daniel Gottschall. I'm with the Mathematics Learning Resource Center here at Villanova, and this is my third video on scaling functions vertically. Okay, so I want to start drawing some more general lessons and the concrete examples we used in the first two videos. So let's go back to video one. And here, recall that we wanted to stretch the function vertically. We use the black function y equals sine x, and we said let's stretch it by a factor of 2. You can see that in the green, where we're basically stretching all the hills to twice their size. And we said we could get that from the function, that graph, I mean, from the function y equals 2 sine x. Uh, so just think about that. So I wanted to stretch the function to twice its size, and I used y equals 2 sine x. So with that idea, if I wanted to say stretch it now to an arbitrary height a, I should say stretch it by a factor of a. So in other words, I want the function to look like this. Um, what function do you think I would need to get that? Just go with your instincts. Don't overthink it. Pause the video if you need a moment to think. And hopefully you came up with y equals a sine x. Right, this is just the natural idea of generalizing from when we wanted to stretch it by a factor of 2. We use 2 sine x, so stretch it to uh, some size a vertically. I want to do y equals a sine x. Alright, hopefully that's clear. And now let's look back at video 2. Was over here. So we wanted to stretch the black function, again, y equals sine x, to the green function, which now is compressed. I might have said stretch, I should have said compressed. Or shrink it. In this example, in video 2, I mean, we wanted to shrink it to half its size, and I said we use y equals 1/2 sine x. So again, think about that for a second. I want to shrink the function to half its height, and I used y equals 1/2 sine x. So what do you think the formula would be if I'm going to use a again? Bear with me, I know it's a little confusing. I'm going to explain myself in a moment. But in other words, let's say I want to shrink this function. Oops. So it looks something like this. Sorry, it's a horrible drawing. I hope you see what I'm getting at here. Essentially shrink all the hills to a smaller height like that, to some arbitrary height a. Now, what would my formula be? Remember, I may shrunk it to half its size by y equals 1/2 sine x. So think about that. All right, and hopefully you came up with y equals a sine x. And now I purposely use a twice. That was a little confusing with the notation. But now notice that when a is in green, we see that we end up with a function stretched larger than sine, I should say with more height than sine x, and then vice versa when a is, like the case where a is red, where we're compressing, we end up with a function smaller than sine x. So what's going on here? Well, in green, we were considering uh, a being greater than 1, because that's implied by the graph. I drew a above 1 in green. Similarly, for the red case, we're considering the case where a is... I'm going to write this and just focus on the second part for right now, where a is less than 1. So like we used 1/2 in the red case as an example of the red situation. When I'm talking about compressing, like we're saying half its size, we could say a quarter of its size, an eighth of its size, whatever, some factor less than 1. And we're thinking of compressing, we always use a positive number, right? That's why I said strictly positive. Like if I want to scale it to the 16th of its size, like I wouldn't say scale it to negative a half of its size. It just wouldn't make really much sense. If we're talking about scaling, where we're stretching or shrinking the same function, we always use a positive number, right? Um, right, so hopefully that's clear. But then you should be asking yourself the question of what would happen, for example, if uh, A were equal to 0, or A being even a negative number, because I just said before scaling that doesn't make much sense, but it turns out we can still work with A in these cases. Alright, so I'll answer the first question in this video since it's actually very simple. So, like, what do you think would happen if I had, let's try it. So, in this case, y equals 0 times sine x. Well, what's 0 times any real number? We know sine x, by the way, it goes from -1 to 1, so sine x is always a real number. What's 0 times any real number? 0. So we would literally end up, I'm going to use actually, let me see here, I guess yellow, just for a different color. Whoops. We would literally just end up with this. Oops, it should be on the x-axis, sorry for my poor drawing skills, but it should just be, right, because y is always 0. So that was easy to answer. We don't really call this scaling though, because you can see now it doesn't look like a sine function anymore because we don't have any hills going on. So scaling, to be clear, is only these cases. That's scaling. But since it naturally raises this question, if we let A be other values, I wanted to talk about these cases. And then what if A is less than 0? Well, I'm actually going to make a fourth video on that because it's worth contemplating more extensively, and I want to keep this video as short as it's supposed to be. I will just note here, we use y equals sine x. These same rules can be generalized to, so basically for any f from R to R, we can scale it. If we want to, instead of using stretching and compressing, just say scale it by a factor of A. We can use the formula A f of x. This will work for any function mapping R to R. It will also work in some other cases. I'm not going to get into that though for the purposes of these videos. Basically almost any, certainly any continuous function, or you can just think of from R to R. Or if you haven't learned that in calculus yet, don't worry too much about this if you're not quite clear on what R to R means. But for those of you that do know, it's just an additional thing to keep in mind. Alright, so this covers scaling, and like I said, I'm going to do a fourth video that's more optional since it's not technically scaling anymore, but just I just wanted to think about that case where A is less than 0. So if you're interested, please watch. As always, come to the MLRC if you have any questions on any of this stuff.